Welcome to Psychology 311, Study Session 11, Audition 3, Vestibular Mechanisms and Sense of Posture. Introduction. Human beings, in common with other vertebrates, possess a set of sense organs that provide information to the brain concerning orientation and motion of the body. They reside in the inner ear and are collectively referred to as the vestibular system. They form a very small part of the human anatomy, the main components being no larger than 10 millimeters across. Most people are unaware of the vital role they play in everyday life, except when something goes wrong with one of the elements of the system. The vestibular system is deeply embedded in the temporal bone alongside the cochlea, which is responsible for hearing and contains two distinct types of sensory organs: the semicircular canals and the otolith organs. Objectives. At the end of this lecture, you should be able to 1. Explain the vestibular mechanism, 2. Describe the sense of posture, and 3. Illustrate how the hair maintain the balance of the body. Pre-test. Identify the functional parts of the vestibular system. 2. Describe the physiology of human sight. 3. How is visual and postural stability achieved by vestibular system? Content. The semicircular canals respond to rotational movement of the head, whether induced passively during activities such as running or riding a horse or a motorcycle, or actively as it occurs when voluntary head movements are made during visual search. Each canal forms a cavity in the temporal bone, and each contains a membranous duct filled with a viscous fluid, endolymph. There are 3 on each side of the head, and the plane of each canal is perpendicular to the others, so that between all 6 of them, they can provide information related to rotational acceleration of the head during movement around any axis. During such acceleration in the plane of a particular canal, the endolymphs tend to remain stationary because of its inertia, so that there is relative motion of the endolymph within the duct. Motion of the endolymph is resisted by viscous friction at the fluid duct boundary and by the elasticity of a gelatinous structure inside each canal, the cupula. The cupula contains sensory hair cells that consequently become deflected, causing stimulation of associated nerve fibers, leading to the transmission of signals to the brain. The otolith organs respond to linear motion. They lie at the point at which all 3 semicircular ducts converge. There are 2 of them on each side of the head, and each contains sensory receptors in a structure known as a macula. With the head erect, the macula in each utricle is oriented horizontally and in the zaccle vertically. The base of each macula carries hair cells that project into a gelatinous substrate in which are embedded minute crystals of calcium carbonate. the otoconia, forming plaque with an area of only 1.2 to 2 millimeters square. The otolith membrane separates this complex from the more fluid endolymph. When linear acceleration occurs in the plane of the macula, the inertia of this dense complex causes it, and therefore the hair cells within it to be deflected in the direction opposite to that of the movement. These deflections set up trains of nerve impulses with frequencies proportional to the extent of deflection. In the otolith organs, hair cell clusters are tuned to different directions of motion, all directions of motion in the plane of the otolith being represented. The utricle can thus send signals to the brain representing a combination of forward and lateral motion of the head, whereas the sacral principally conveys information about vertical motion. Maintenance of visual and postural stability. In general, the function of the vestibular apparatus is, via connections in the brain, to generate activity in various muscle systems, which will compensate for the head and body motion and result in the maintenance of visual and postural stability. The area in the brain stem, the vestibular nucleus, that receives the output of the canals and otoliths that direct connection with muscles controlling eye movement and with muscles of the neck and limbs. In the case of the eyes, the vestibulo-ocular reflex generates eye movements that compensates for head motion with a very short delay, around 10 milliseconds. When we walk or run, the head generally bobs up and down. Stabilization of the eye prevents movement of visual images of the retina, which would otherwise cause images to be blurred. Individuals who have been unfortunate enough to lose the function of the vestibular system through damage to the inner ear often experience apparent notion of the visual world. Oscillopsia. Under these circumstances, fortuitously, the vestibulo-ocular reflex, designed to deal with maximum running speed, also allows modern man to view stationary objects in the outside world when traveling in high-speed vehicles, where there is often considerable linear and angular vibration. However, sometimes the reflex is inappropriate. Reading a newspaper in a train is often difficult because when looking at objects within the moving vehicle, the stabilizing reflex is no longer appropriate. To suppress the eye movement, we rely largely on the ocular pursuit system, a mechanism that we normally use to track moving objects with the eyes when we are stationary. When ocular pursuit has a very limited range of operation and does not function at frequencies of vibration about 2 cycles per second. Unfortunately, in moving vehicles, frequencies of vibrations are frequently much higher, between 2 and 20 cycles per second. Stabilization mechanisms similar to those for the eye operate for control of the head, limbs, and other postural systems, but they are necessarily more complex than those controlling the eye. Perception of motion and orientation, as well as controlling actions within the body. Vestibular stimulation also engenders powerful sensations of motion and orientation in space. Stimulation of the canals give a sensation of turning, so that someone who is rotated on a swiveling chair will experience a sensation of rotation even in the absence of any other cues, such as vision, for example, with their eyes closed. However, because the canals are really responsive to angular acceleration during a constant rate of angular rotation, constant angular velocity, the sensation gradually decays over 10 to 20 seconds. As rotation stops, the individual experiences rotation in the opposite direction, even though actual motion has ceased, because the fluid in the canal continues to move when the head has stopped. In everyday life, prolonged rotation is not often encountered, but it does not occur frequently when flying. Pilots must therefore be aware that they cannot always rely on the sensation of motion, particularly in circumstances where there are no other reference cues such as sight of land, for example when flying in cloud. Stimulation of the otolith organs also gives rise to sensations, but in this case they may be of either linear motion or of orientation with respect to the vertical. When linear acceleration is sustained, it causes a continuous deflection of the otoconia. The most common situation in which this occurs is when the head is tilted. When gravitational acceleration causes the otoconia to be deflected in proportion to the degree of tilt. Consequently, application of sustained linear acceleration is usually interpreted as tilt, so that when accelerating forward in a high-speed vehicle, a sensation of being tipped backward is experienced. Again, this is particularly important when flying because on takeoff, an aircraft is normally accelerating and climbing at the same time. The combination of the vehicle and gravitational acceleration gives rise to a sense of tilt that is greater than it should be, and the pilot must learn not to misinterpret this sensory information. When linear motion changes frequently, for example during vibration, a true sense of linear motion is normally experienced. This is most sensitive as frequencies close to those of natural head movement, around 2 cycles per second. In normal circumstances, linear and angular motion stimuli are combined, as when we bend down to tie a shoelace in a moving train. In such circumstances, the sensations can be complex and unexpected as a result of the Coriolis components of acceleration that accompany motion in 3 dimensions. The individual may experience a disturbing sensation of tumbling in these circumstances, which may be sufficient to bring on motion sickness. Allied to the experience of linear or angular body motion are similar sensations that may arise from motion of the visual world when the body itself is stationary. These sensations of self-motion are referred to as linear or angular vection, respectively. Disorders of the vestibular system. One of the major consequences of a failure of the vestibular system is the occurrence of vertigo or dizziness, which is experienced by large numbers of individuals. Acute vertigo can occur when the vestibular system on one side of the head suddenly stops working effectively. which can be due to factors such as vestibular neuritis or hemorrhage in the cerebellum or brainstem. In such cases, there is sudden onset of a strong sense of rotation, often accompanied by flicking back and forth of the eyes. Nystagmus. It generally disappears within hours or days. More persistent vertigo can occur, for example, as a result of the migration of calcite, crescite, from the otolith organs on to the cupula of the semicircular canal. The cupula then becomes inappropriately sensitive to gravity, and a sensation of turning is brought on by change of head position with respect to gravity. There are other examples of clinical problems arising from vestibular failure, many of which cause great disturbance to the sense of the body in space. The hair and balance of the body. The semicircular canal begins from the vestibule, goes around and rejoins in the vestibule. Some particles of the calcium carbonate called otoliths are found near the hair cells of the ampullae and vestibule. The movement of the head in any direction can be detected by the receptor hair cells. The nerve fibers coming from these two types of receptors reach the cerebellum through the auditory nerve. Summary. In this lecture, we have learned the vestibular mechanism and the sense of posture. We are able to identify the functional parts of the vestibular system, explains the mechanisms underlying the perception of motion and orientation, the visual and postural stability, and finally, the likely odd disorders that may occur in the vestibular system. This is the end of study session 10. Thanks for listening.